This video is going to deal with improper integrals. So it's kind of the last, I hate to say new integration technique because it's not really new. We're just going to put together two things you already know how to do. So they're going to be called improper integrals. Now, so far you've had kind of two kinds of integrals, indefinite and definite. Remember what indefinite are. Indefinite didn't have numbers on the integration. So you didn't have a number A and a number B. All right, so on those indefinite integrals, you got functions, and then you have that plus c. So really, you got a family of functions. Then remember when we went to definite integrals, that'd be you integrating from like -1 to 5 of a function. So you would get numerical answers. So you got a family of function on indefinite integrals, and you got number answers on definite integrals. Well, improper integrals look like definite integrals. The only difference is instead of having numbers for a and b, either a or b or both has an infinity on it. So it's going to sort of be like Cal 1 meets Cal 2. So you're really going to combine two things you already know how to do. So let's pull up the PowerPoint and kind of start working our way through it. Okay, here we go. So improper integrals. So just kind of to reiterate, improper integrals have infinities instead of constant numerical values for a or b or both. So like I said, it's going to kind of be a combination of Cal 1 with limits and Cal 2 with integration. So if your f is continuous on the integral from a as a number, like a constant, to an infinity, then what you're going to do is you're going to change your number to your infinity. You're going to place that infinity with a variable. It doesn't matter which variable. Usually, because you're accustomed to having a's on the bottom and b's on the top, they tend to follow that through. So because the number on the top, so to speak, is the one you're quote missing, they replace that with b, and then b approaches infinity. So it's your new thing approaching your original of your function. So you'll just do this integration the way you normally do, and then take the limit at the end. Similarly, if you're going from -infinity to a number, say b, when you're integrating from -infinity to a number, again, that infinity gets replaced with a variable. So that -infinity got replaced with an a, and that's your new thing, a approaching your original -infinity. Now, what happens if you've got infinities on both? Well, basically, you just divide it into a sum of a and b. So you go from -infinity to some convenient number c, and then from that same convenient number c to infinity. Now remember, since it's kind of like working a definite integral, you're going to be substituting those numbers into your answer after you integrate it. So pick an easy value like zeros, ones, pi's, those kind of things. Just, it doesn't really matter. So I might be going from -infinity to 0 and then 0 to infinity, or -infinity to pi and then pi to infinity. Everybody's c doesn't have to be the same choice. Let's go work 2 or 3 just to kind of see what we're talking about. All right, look at this first example. On this first example, I'm going to integrate 1 over x dx, which you've done now so many times. But the difference is, to go from like 2 to 5, I'm going from 2 to infinity. In other words, I start at 2 and I just keep going forever. So what I do is, because I'm replacing the one on the top, that's why they chose b. And b is really infinity, so we're going to do the limit as b approaches infinity. Now, when you're doing this integration, when I see a fraction, the first thing I think of is natural log. So sure enough, the derivative of that denominator x is 1. It's sitting on top. So when I do this integration, I just get natural log of x. Okay? Now, really, it should have an absolute value there, just to kind of reiterate. Okay? Then I substitute in my b. So it's really the natural log of the absolute value of b. But since I'm on the positive side, that's a little redundant. Okay? But still, it's better to be exact. Now, the natural log of 2 is just a number. Now, what's the limit of a number? Well, the limit of a number is just that number. The limit of 5 is just 5, regardless of what you're approaching. Now, don't get limits confused with derivatives. Remember in Cal 1, limits of constants are that constant. Derivatives of constants are zeros. So keep that in mind. Now here, look what happens. B is getting bigger and bigger. So the natural log of 10, natural log of 100, natural log of 1,000. Now, you may have forgotten what natural log looks like, so I just went and graphed it real quick over here. And notice, when your numbers get bigger, the logs of those numbers get bigger. So as b gets bigger, the natural log of b gets bigger. So that's why this answer, the limit of bigger numbers, the natural log of numbers that get bigger, those natural logs also get bigger. And then remember, infinity is not a number. It just means this value is getting larger and larger. Now, you're taking off a tiny amount. Does that tiny amount really do anything? It just kind of slows this down. So instead of going from, say, 10 to 100, maybe I'm going from 9 to 99. Still getting bigger, okay? So the infinity minus this small value just stays a number that gets bigger and bigger and bigger. So the limit doesn't exist right there. Remember, that's what we talked about in Cal 1. When you get an infinity answer, we're not saying the limit doesn't exist. I mean, we're not saying the limit exists. We're saying the limit doesn't exist and why. This limit does not exist because the answers are getting larger and larger and larger. You're not converging on a number. So that's why when you do this integration, you get an infinity kind of answer. They're going to say that the integral diverges. So it diverges when you're getting infinity answers. It's going to converge when you get numerical answers. Let's go look at a different example. Okay? So let's go look at example 2. Again, the integration is not going to be a problem. So again, I'm changing the value on the top. So they replace that infinity with a b, and then the limit is b approaches infinity. Now, similarly on this one, my first thought is natural log, but you know, the derivative of x squared is going to be 2x, and I can't get a 2x. So it's not natural log. So the next thing I notice is, well, I've got a power. Maybe it's power rule. But when it's power rule, remember the power needs to be on the numerator. So I brought it up. So remember, when you bring a variable from denominator to numerator, or numerator back down to denominator, then it's going to change the sign on that power. So that's why that 2 became a -2 when I brought it up. And then again, that 3 I just pulled out front. Now this integration is like we've always had, okay? So when you've got something to a power, you need the derivative of the inside, but the derivative of the inside is just a 1. So it's just power rule. With power rule, remember, you add 1 to your power. So -2 plus 1 is a -1, and then remember, you divide by that same power. Now here all I did was use a limit rule from Cal 1. I can take numbers and pull them out front of integrations, but I can also take numbers and pull them out front of limits. And that just seemed the easiest and, you know, just an easier way of looking at it. You could have left it in, but I think it's just easier to look at the graph and see this. Remember what happens? X is getting bigger and bigger and bigger. All right. So I put b in first. You know, definite integrals, that top number goes in first, minus, and then that bottom number. So when I put a b in there, I get a -1 over b, and then it's always minus. And when I put a 1 over there, I get that -1 over 1. Okay. So minus a negative turns into a plus. Okay, and of course, 1 divided by 1 is 1. So it shouldn't be a surprise. The limit of a constant is that constant. But let's make sure we understand this. This b is getting bigger and bigger, like 10. So -1/10. Maybe it goes to 100, -100, -1,000. So do you see as b gets bigger, the fraction gets smaller and goes to 0? See, look over here. As your value gets bigger, that fraction, when you put 1 over it, gets smaller. 1/10. If you go to 100th, it's smaller. 1,000th is smaller. And then, of course, 0 plus 1 is 1, and 3 times 1 is 3. So again, this time I got a numerical answer. That limit existed. When I get a numerical answer, they're going to say the integral converges. All right, let's look at one more. Well, let's go back, share the screen again, and let's go look at this next example real quick. Okay. All right. All right. This is kind of some trig thrown in there just to kind of make sure we review some things from Cal 1 again. All right. We're integrating this. Now, again, the first thing I would try probably is natural log, but the derivative of that denominator, that'd be the derivative of 0, so that's not a problem. But the derivative of e to the 2x would be e to the 2x times a 2. In other words, 2e to the 2x. Well, getting the 2 in front wouldn't be a problem, but see, I don't have e to the 2x, I have e to the x. So that's not going to end up being natural log. It's going to end up being arctan, and I'll show you that in a second. But what happens when you're integrating from a negative infinity to infinity? Well, I've got to break it up from negative infinity to some number that's pretty easy, and from that same number to infinity. Now, why did I pick 0? Because I knew in a minute I'm going to be substituting 0 in for x, and I really like powers of 0. You could put in a 1 or a 7 or a negative. It wouldn't matter. You just pick a convenient value, but 0 seemed like an easy number. So that's why I went from negative infinity to 0 and then 0 to infinity. Then remember, this gets replaced with a variable. When it's on the bottom, they tend to replace it with a, and do the limit as a approaches negative infinity. Okay, that same integrand. And then I go from 0 to b, because they picked b because they're replacing the top thing. And then the limit as b approaches infinity. Now, when I started looking at this, it wasn't natural log, it's not power rule. And then suddenly I remember, what about those inverse trig functions, those arc functions? And remember, with arctan, you had an a plus a u squared. So that's what I mean over here. I wouldn't kind of put it in that form. 1 is 1 squared, and e to the 2x is e to the x squared. Remember, when you have a power raised to a power, you multiply them. And x times 2 is 2x. So this is an a squared plus a u squared, so it's arctan. So my a is my number on the inside, so a is 1. Now, u is not the whole thing. Remember, u is what's on the inside that you're squaring. So my u is e to the x. Now, remember, with arctan, you need dx on the top of the differential. So I need the derivative of my u. Well, what's the derivative of e to the x? Well, the derivative of e to the x is e to the x. So this ends up being arctan. Now, you might have to go back and look in your books at the formula. But remember, the formula for arctan is 1 over a. But see, 1 over my a is a 1. 1 over 1 is just 1, so I just wasn't showing 1 over a. And then arctan of u over a. So my u is an e to the x, and again, over my a is 1. But e to the x over 1 is just e to the x. So that's where that kind of came from. Okay, let me clear that out so it's not distracting you. Okay, all right. So that's why I get arctan e to the x here, and that's why I get arctan e to the x here. And then my limits just kind of come down. So the limits just come down until after I do the integration. See, I'm still not finished with the integration. I've got to do my f of b minus f of a. So when I plug 0 in first, I get the arctan of e to the 0. It's always minus, and then the arctan of e to the, that goes in a. The same thing over here. That b goes in first, and then that 0 goes in last. Now let's review Cal 1 for a minute. Remember, you're used to doing tangent of angles equals numbers. So used to angles coming in and numbers coming out, but on inverse functions, those domain and ranges switch. So instead of angles coming in and real number answers coming out, the real number answer, so to speak, is coming in and the angle's coming out. So it's asking you what angle has its tangent to be e to the 0. Now, what's the same thing as e to the 0? What's e to any number? All right, e to the 0, any number to the 0 power except 0 to the 0 is 1. So that's really arctan of 1. So it's asking you what angle has its tangent to be 1. Now think about it. Remember your special triangles, okay? Do you remember that when you have a right triangle and you've got a 45, 45, that's a 1 and that's a 1. And then remember this side, that's hypotenuse, is the square root of 2, okay? So opposite over adjacent, 1 over 1. So that must be a 45-degree angle. That's the angle whose tangent is 1. So I put pi over 4 because remember they want it in radians. And pi divided by 4 is 45 degrees in radians. Now what I did over here was I went and kind of redrew the trig equation. This is the graph of y equals tangent of x from negative pi over 2 to pi over 2. Because that's where kind of arctan's defined, okay? Now look right here, all right? What happens when this a comes in, but that a is a negative number, okay? So it's like negative 10, negative 100, negative 1,000. So do you see that would be like a 1, and I went over, in my mind, kind of e to a positive number. Because if I'm putting in a negative exponent here, when I bring it to the bottom, it's a positive exponent. So that's like e to the 10th, about 3 to the 10th power. around 3 to the 100th power. Do you see that that bottom's getting bigger and bigger, so that fraction's getting smaller? So that's why that went down to 0. All right, so this right here, I'm looking at the graph. Where's the tangent getting close to 0? Well, the tangent's getting close to 0 right there at 0. So that's why that's a 0 right there. Okay, the arctan of 0 is 0. Now look at this one. This B is positive, so this is getting bigger and bigger. Okay, so where does tangent get bigger and bigger and bigger? Do you see that tangent gets bigger and bigger and bigger? Remember, there's an asymptote right here. So when I know that the tangent's getting bigger, the angle I'm getting close to is pi over 2. So that's why there's a pi over 2 right there. And then minus, and again, this e to the 0 is the same thing as 1. So where is your tangent 1? What angle has its tangent 1? Well, the angle that's got its tangent to be 1 is pi over 4. Well, do you see that that's a positive pi over 4 minus a pi over 4 goes out, so I'm left with pi over 2 for my answer. It's a number answer, so the integral converges. Now that's kind of as nasty a one as you would see, because you've got e's with arctan, a lot of cal 1 back in here with this cal 2. But as far as doing improper integrals, all you're going to do is replace those infinities with the variable, and then let that variable approach the infinity that you replaced it with. Okay? Then work the integration the way you normally would, and then take the limit at the end. So try that homework. If you have any trouble, then make sure that you contact me. All right, like we've said before, you can stop anytime you want to. Email me. We can set up a one-on-one Zoom meeting. You can send me pictures of your work back and forth. I don't think you're going to have any trouble with the improper integrals. It's just a little bit of cal 1 meets cal 2. Let me hear from you.